Good morning to the head of the department mechanical engineering, Professor A.K. Chaturvedi sir, my seminar guide Professor Brijesh Tripathi sir, to all the faculty members and all my friends. My name is Harish Gurjar, final year aeronautical engineering student, and today I am presenting a brief on my seminar topic Lattice-Boltzmann methods for single phase and multi-phase flows in supersonic conditions. So now let us see what we will go through in this whole presentation over here. So going through the content and overview, first we will see the Lattice-Boltzmann methods introduction, then we will go through the equations that are used in Lattice-Boltzmann method. Later on we will see the advantages and disadvantages of this method, different flow phases and where we apply the Lattice-Boltzmann method as well. We will also see how versatile this method is, that the different areas where we use Lattice-Boltzmann method, and then we will see a comparative diagram where the Lattice-Boltzmann method is compared with different other methods and where on what scale does it lies. So moving ahead, let us see go through the introduction of the Lattice-Boltzmann method first. So till now in computational fluid dynamics, or I'll say in numerical simulations, we have seen two approaches. The first one is continuum approach, where the particles are considered as the continuum, and then we will methods like finite difference method, finite volume or finite element method, we solve Navier-Stokes equations. The other method is molecular approach, where using molecular dynamics, or we will say microscopic scale, where each and every particle is tracked and the momentum equation, Newton's momentum equation, is solved, and with the help of that we gain the change in physical properties like temperature, pressures, etc., etc. But what if there is a middleman? So here comes the middleman, which is Lattice-Boltzmann method, which incorporates properties of both macroscopic scale, which is continuum scale, and the other one is molecular dynamics, which is micro scale. So what we do in this, which is known as mesoscale. So we do mesoscalic modeling over here. So let us see how this works. So in Lattice-Boltzmann method, what happened, we describe a distribution function. A distribution function is a function that represents the properties of the collection of particles. So through this distribution function we will get all the physical properties of the particle. However, the Lattice-Boltzmann method is a probabilistic model in which we see the probability of the particle to be present at a particular given space with a particular given velocity. So of velocity or speed, I will say. So going ahead, and let us see how equations of the Lattice-Boltzmann method works. So over here we see discrete kinetic equation. As I said, Lattice-Boltzmann method is a mesoscale approach. So here it is derived from the kinetic equations, I will say, or lattice gas autonoma. It is a derivative of lattice gas autonoma over here. So in this discrete kinetic equation, what I see, that there is a term Fi and then there is a term Om-I. So both are these are discrete over a particular lattice, and then we will see that what is Fi, it is a distribution function, and the Om-I over here, it is a collision operator. So both these terms are very important to track down the property of the particle. So how we track down the property of the particle using Lattice-Boltzmann method? So it is very simple. We track down the evolution of this distribution function over here, and then with the study of the evolution of the distribution function, we get the properties of the particles over here. So let us now understand what is lattice arrangement that is used in Lattice-Boltzmann method for the discretization purposes. So lattice arrangement is represented by some term D and D subscript N and Q subscript M. So what does this mean? So D represents over here dimension, and N is the number of dimensions like 1D, 2D, 3D. And then we go ahead and if we talk about M is the speed model, that how many speeds at which the particle can be discretized. So this represents that, for example, D1, Q2. So the dimension is 1D and the speed at which the particle is discretized are two speeds present over there. Now let us go through the advantages of the Lattice-Boltzmann method, which is very important to use this method as numerical simulations other than different other models that are present. So first is easy implementation of the Lattice-Boltzmann method. So Lattice-Boltzmann method is relatively very easy to like implement on the flow phenomena. Other one is its ability to simulate complex fluids like multi-phase flow, polymer, suspensions, etc., which is very good. I can say that it can simulate multi-phase flows as well. The other one is adaptive grid. So it's like it has a regular grid structure that can easily adapt complex geometries, which is also an advantage over here, we can say, of this Lattice-Boltzmann method. Other one is accuracy. So for higher order discretization, we can achieve good accuracy of the Lattice-Boltzmann method. Conservation laws are already incorporated in it. Then we will say parallelizability. So over here, if we talk about parallelizable, how parallelizable the Lattice-Boltzmann method is, so we can say that it can take advantages of multi-core processing as well. It is more related to the hardware, if I say, or like computing architecture, I will say. So it can do parallel computing as well, and as it is very easy to implement, it gives advantage over here. The other one is reduce numerical diffusion, and the last one is boundary conditions. So we can like wide range of boundary conditions can be incorporated in it easily, like no slip condition, moving boundaries, and etc. So moving ahead, and let us see what this particular term multi-phase flows are over here. So for that we have to understand what are flow phases. So we already know that what are flow phases, or like solid, liquid, gas, we know that, but what does multi-phase means over here? So first we talk about single phase fluid, where we only in classical fluid dynamics we see that water, air, steam, etc., that has single phase, that is maybe they are gas, maybe they are liquid, or maybe they are solid. But if we go ahead and see multi-phase flow, then in multi-phase flow we deal with the different kind of flows. Like one is liquid, other one is solid, maybe other one is gas, and one is liquid. Like when a bubble is coming out of boiling water, it is like dealing with. We are dealing here with two phases. One is the gas phase, steam, and the other one is water itself, liquid phase. So in multi-phase flow, we deal with mixture of two phases like oil phase one, water phase two, like that, and then other mixture of like different fluids. Then second one is phase changing processes like boiling, evaporation, and all that. Over here we can deal with phase changing materials as well. Other one is phase interface. Two phases are in uh, dealing with each other, so we will see the phase interface of that too. So for example, bubble, vapor explosion, drop of water, etc., etc. So moving ahead, in with this, let us see advancements and versatility of Lattice-Boltzmann method. So this slide is particularly very important to understand how versatile the Lattice-Boltzmann method is. So going ahead, and let us see these five sections over here. These five sections describe how versatile the Lattice-Boltzmann method can be, and the type of methods or models that can be used in Lattice-Boltzmann method to solve different kind of flow phenomena. So first we see flow turbulence simulation over here. So in flow turbulence simulation, DNS, which is direct numerical simulation, using Lattice-Boltzmann method, is done. The second one, which is used as subgrid scale model, incorporated with Lattice-Boltzmann method, is more related to large eddy simulation terms. So these were the two mostly discussed models, we can say, Lattice-Boltzmann method for flow turbulence simulations. Moving ahead with multi-phase and multi-component flows, which is very important over here. So firstly, I can say DNS was the first term that is used for simulating multi-phase and multi-component flows, but it was able to simulate only low Reynolds number flows over here. Then later on, with some advancements, uh, what three different models were created. One was the color model, where different type of phases were represented as two different colored distribution function over here. Then the second one is pseudo potential method, and the last one was free energy approach, which was the first thermodynamically consistent method used in Lattice-Boltzmann method. Moving ahead with compressible and shockwave simulations. Over here, shockwave and compressible flow is something that still needs further study to understand the potential of Lattice-Boltzmann method, because no further studies was done. Like I will say, no more studies are done to use this method in their compressible and shockwave simulations over here. However, there were different models used to understand the compressible flow and shockwave using Lattice-Boltzmann method, but it still needs the validity of those methods as well. To prove that Lattice-Boltzmann method is a potential numerical method to simulate compressible and short-wave flows. Now we go through heat wave, reaction, diffusion, and phase transition phenomena. So there were two mostly used methods. One was multi-speed Lattice-Boltzmann thermal model, and the other one was enthalpy-based Lattice-Boltzmann method. These two methods were the one that were most discussed to uh, simulate heat transfer, reaction, diffusion, or phase transition phenomena over here. And now we discuss about a different kind of approach, which was finite difference lattice Boltzmann method, which was used to simulate flow using unstructured grid over here. So this was the one method that can also be used to simulate compressible and shockwave simulations over here, but yet further study is needed for this. So moving ahead with the disadvantages of the lattice Boltzmann method over here. So first is the limited applicability. Like it can be applicable to the a small range of phenomena, which is described in the second, which is limited scalability. So in this, a certain type of problem, especially like high viscous flow, low Reynolds numbers can only be simulated. For further, many other different advancements are needed to simulate high Reynolds numbers and all that. Moving ahead, it is very complex for a beginner to understand Lattice-Boltzmann method sometimes, because as it is in meso scale, so we deal with both continuum and particle dynamics at the same time. And the other one is it is subjected to sometimes numerical instability and numerical errors as well. So moving ahead to with the presentation, let us see the comparative diagram of different simulations tools that we have right now. So over here we are discussing about the Euler's approach, Ran's model, large ED simulation model, direct numerical simulations method, Lattice-Boltzmann method, DPD, DSMSC, and molecular dynamics over here. So we have described all these models using a scale which is represented by Knudsen number, continuum and non-continuum approach over here, like one where we have understand the continuum based methods that understand fluid as a continuum, finite difference method, finite volume, and solve numerical Navier-Stokes equation over here, discretized Navier-Stokes equation over here. And where on the other scale we will see all the particle dynamics method that take a particular particle and then solves the Newton's laws and then get the properties of the particles. But here we can see that Boltzmann equation is the one that can simulate all the approaches. One is continuum based approach and other one is particle based approach that we have discussed in the slide number 1, where I was giving the introduction of lattice Boltzmann method over here. So let us move ahead with the conclusion of this, and over here we can say that Lattice-Boltzmann method is a probabilistic method where we see the probability of the particle to be present at a particular given position with a particular given speed. So it is simple to implement, yet apply to a finite range of flow problems only. Ability to simulate complex boundaries such as multi-phase, multi-component flows, and also a potential tool for such flow simulations over here. But yet if we talk about conditions like supersonic conditions, on all that, many models are developed but yet need a different kind of further study to understand the potential of lattice Boltzmann method to simulate supersonic fluids and all that. So this is the conclusion of the whole